right, so this is section 6.1, part 1, because we're going to kind of strip this down into 2 different sections because it's quite long. And exponential functions is the first topic for this chapter, and then later we'll get into logarithmic functions. So the first thing we need to do is define what an exponential function is and what it means to grow exponentially, because these are words that are used kind of in common discussion a lot of times. Oh, it grew exponentially, which means, it grows really, really fast. But what it actually means is it grows with a specific multiplicative rate, right? So a percentage change is the constant rate of increase rather than a linear change. And so here are some vocabulary words for you. A percentage change is a change based on a percentage of the previous or original amount. Exponential growth is an increase based on a constant multiplicative rate over equal intervals of time. And I'm going to show you what that means in just a second. And decay is just the decreasing alternative, right? Rather than growth, we are decaying if it's decreasing. And so looking at linear versus exponential, sometimes it's easier to understand what I mean by all of those words that I said in the definition previously. So if we look at these 2 tables of values, so you here have the x or the inputs for 2 different functions. This one is exponential. Notice the exponent is a variable, and this one is linear, which is something that we're familiar with. It has the rate of change in front of the x. And so the way this particular linear function grows is it increases by an added amount every single time in terms of the output. So the slope is 2, or the rate of change is 2. And what that actually means in practice is that for each output value that corresponds to an increasing input value, we just add 2 every single time to get to the next value. It's growing by 2 every time the x or the input grows by 1. Now, alternatively, the exponential function does not grow by adding. It grows by multiplying in the outputs. So what we're doing here is the base is 2, and that's the multiplicative rate of growth. So we're going to multiply by 2 every time. So 2 times 2 is 4, and 4 times 2 is 8, and so on and so forth. So whereas with the linear function, we are adding the growth rate, here we are multiplying by the growth rate, which is why exponential growth occurs so much more quickly than linear growth does. Again, increases in linear by the same amount over equal increments in the domain or the input values, and the exponential function increases by the same percentage over those same equal intervals in the input values in the domain. And so that's the difference. We'll be discussing the exponential today. So this is a general exponential function. This one in particular is a really common exponential function, y equals 2 to the x in this picture here. In general, here is a set of characteristics for any exponential function. So we take the output, f of x, is equal to a, some number that is not 0. A is the initial value, and b is the growth or decay rate, or the multiplicative growth rate. It cannot be 1, and it cannot be negative. So again, you can note here, b is positive and not 1. So looking at the graph, it's easier to see the domain. The domain is all real numbers from negative infinity to positive infinity, and the range is all positive real numbers if the initial value is positive, and if it's negative, then this function would flip over and it would be decreasing instead. But this is a positive a value. In this case, the a value is 1, b is 2, and then the x is in the exponent, as with any exponential. Of importance is that the y-intercept is 0, comma a. And so again, let me rewrite this for you so you can see the a value. This function is f of x equals 1 times 2 to the x. And so this is a. this is B. And so as you can see here, the y-intercept is always 0, comma A. And so that stands here. This would be 0, A. And then the horizontal asymptote, there is one. Notice here this function, like if you're moving to the left, it's getting closer and closer to a particular value, and that value is the horizontal asymptote of 0. And so all of those general characteristics will be helpful to us as we move on. Example number 1 is just, when is something an exponential function? And remember, the key idea here is that the variable is in the exponent. Okay, so that's what we are looking for in the exponent. So examining these 4 examples, we'll see that this one is not, this one is, and this one is. Notice here there's a number in the exponent and there is no variable. All of these have an x in the exponent. And so if you want to try number 1, I've already highlighted the answers here for you. You will see that g of x and f of x do in fact have those variables in the exponents here and here, whereas h of x and f of x do not. This is your standard quadratic. This is a standard linear function. Next, we'll evaluate exponential functions, which is pretty standard stuff. Remember, when we evaluate, that means we just plug in some input value and get the corresponding output. So if this is the given function f of x, to find f of 2, I will simply replace all the x's with 2's. Now, one thing I want to point out, and the reason that I include this example, is to make sure we are following the proper order of operations. So let's remember that. This is, your standard PEMDAS that we all remember. So the first thing is parentheses or any grouping symbol, right? That's up here. This is grouped together, so we'll need to handle that first. So the first thing I'm going to do is I'm going to change that 2 plus 1 to a 3. The next thing I'll handle is any exponents. This value has an exponent attached. The 5 is multiplied, so I'm not going to do that yet. So this becomes 5 times 3 to the third, which is 27. From there, I will then move to multiplication, and 5 times 27 will give me the final answer here, which is 135. But if you're not following the order of operations, sometimes you might do 5 times 3 and then do that to the third power. That's not going to work. And that stands for your calculator usage as well, because you are going to have to you can plug all this in, and your calculator may or may not follow the proper order of operations depending on what you're doing. So make sure that you're aware of what steps to take first. So if you want to try number 2 and make sure you can get what I got, I encourage you to do that right now. Pause the video. In this unit, we're going to be rounding to 4 decimal places. And so that's just something that's kind of become standard and that will follow us through this entire section. So next, we're going to move on to talking about exponential growth in particular and writing equations from scenarios. So as we discussed previously, for an exponential function, f of x equals a times b to the x, a is the initial value, as you can see there in the bullet points, and b is the growth factor per unit x. So if the unit is time, for example, you can imagine that that will change from an x to a t just to keep track of what we're dealing with. So here's a lot of words. Let's read them. So the population of India is about 1.25 billion in the year 2013, with an annual growth rate of about 1.2%. This situation is represented by this growth function. So look, if you just keep reading all the words, you'll see that they already gave you the function. You don't even have to write it. And then it defines t as the number of years since 2013. This is not the first time we've seen this idea of defining a year where t is equal to 0, which is the starting time. And we're going to find that that is particularly useful in exponential functions a little later on. So all we want to know here is to the nearest thousandth, what is the population of India in 2031? So the only step we really need to take here is recognizing that in 2013, t is equal to 0, because that is our initial starting value. for time. So from there, I'm asking you what it's going to be in 2031. So I need to determine what the input value will be that corresponds to the year 2031. Well, to find that, I'll say 2031 minus 2013, and I'll determine that the difference in years for this is going to be 18. So t is equal to 18 if 2013 is 0. So now I have a value for t, and I can evaluate the function at that value just like we did in the previous example. So I just plug in 18 for t, follow the appropriate order of operations, and from there we'll obtain the population in the year 2031, which is going to be approximately, again, to 4 decimal places. Let's see. Actually, I have it to 3 here. Hold on, let me redo it. This would be 1.012 to the 18th power times 1.25. Okay. So this would be 1.5494 billion. I want to make sure I kept track of what I was asking you to do. I had 3 when I worked it out before. So population in 2031, 1.5494 billion. And now you give it a try. So here's another big bunch of words, but read through, understand that they are giving you the function and then just asking you to evaluate at a particular t or year. And then it's also asking you to make a comparison to the prediction we made in number 3. So if you want to pause the video, see how you do, check your answers here. All right, so moving on to the next section. Instead of evaluating functions, now we're going to find an equation for an exponential function. This how-to box is here so that when you're going back through the notes, you have a very, very clear set of steps to follow to do any problem in this section. So example number 4, writing an exponential model when we do know the initial value. So recall that the general format for an exponential is f of x equals a times b to the x, where a is the initial value. So here we know a. Okay, so in 2006, 80 deer were introduced into a wildlife refuge, and by 2012, that population had grown to 180. This population is growing exponentially. Write an exponential function representing the population over time. So the first thing I want to do is I want to get a handle on what my function is going to look like in general. So instead of f of x, I have n of t, and then a times b to the t, because instead of x's, I'm using t's in this particular function because the units that we're looking at are time. And then just remind yourself that a is the initial value of the function, and b is the growth factor. So in order to figure this out, I'm going to go ahead and kind of put in what I know. Well, what do I know here? Well, I know the initial value, which is 80 deer. So I'm going to go ahead and make that replacement and then remind myself over here that a is 80 just for later. So now, what other number do I need to complete this function? Well, I need to find b, the growth factor. And I can't do that with this information by kind of dividing or getting a percentage, because this is not an equal growth rate every year. The rate actually, the increasing amount is different. So what I need to do is I need to use a given input-output pair. So let me make that note here. Use a given input-output pair. Input-output pair. Well, maybe that's not obvious. Wow, that's amazing what I just did. Input-output pair. Input, out. I just combined all the words. Input-output pair. So let's make a list of those. T's and N of T's. Well, remember when we're working with exponentials, I call the starting point year zero. And so what year is that? That's going to be 2006. So let's make a column for the year. And in 2006, what is that population? Well, that's 80. That's how I got my initial value. Recall that the y-intercept is at 0a, and that's the initial value a. That's why it's important to redefine the inputs from year to years since 2006. So it's easy to obtain the starting value. Right, so the next input output pair I have is going to be 2012 and 180 deer. But I need this in terms of T, which is years since 2006. And so T would be 6 in this case. So the input output pair that I'm interested in is 6, 180. Well, what do I even do with this now? Well, the input is T and the output is N of T. So now I can just plug this in to what I already have to solve for B. And then once I do that, I'll have an A and a B, and I can write my function. So the next thing I need to do here is isolate this variable. And to do that, I'm going to divide by 180. So what I'll end up with here is 9 over 4. And so one of the important things in this particular type of problem is we do not want to round or do a decimal approximation until the very end. So you'll see me leaving fractions and stuff like that in until we're done. Now, how do we solve for B here? So going back over on the side, let me look at something with you. So if I had 4 equals x squared, I would take the square root of both sides in order to solve. What I have here is a power of 6. So I will need to take the 6th root of both sides to solve for B. Now, at this point, your calculator will perform this operation, and I'm going to show you how to put that into your calculator real quick. So if we are trying to calculate the 6th root of 9 over 4, what you'll do is you'll hit the number 6, and then you'll access this green function x root by hitting second caret, which is the up button. Notice now I have a 6th root, and I can place the fraction inside using the normal fraction button, and that will calculate the 6th root for me, which is approximately 1.1447. And so that's how to calculate a root that's not a square root in the TI-30 calculator. And so just pulling that out, remember at this point we're going to round to 4 decimal places. So this would be 1.1447. Start that over. 1.1447 is my approximated or rounded value for B. These are long problems, so you really have to stay organized to be successful here. That's why I do things like this. I keep track of what is A and what is B, because I know that ultimately that is what I will need to write my function. So once I have A and B, I can write my function just by plugging these values into the basic template. So the function is N of T equals 80 times 1.1447 to the T. And that is the function that models this situation with the deer and the population growth. So again, to recap what we did, because we did a lot, and I explained a lot of things as we were going, but to look at it as a whole, I know that I need to write this function. I know that A is the initial value and B is the growth factor. I know A, so I will go ahead and plug that in. I still need B. And the only way to find that with the information I'm given is to use an input-output pair, because I am given those. The input for this function should be in terms of T, not the year. It should be T defined as years since 2006. That makes t0 gives me automatically an initial value, or the y-intercept. And then I'll calculate the other input-output pair in terms of t years since 2006, giving me 6 years since 2006 for this value. Once I have a matching pair other than the intercept, I will take that and plug it into the initial piece of the function that I wrote. Then I will be able to solve for b, which is the other parameter that I need to write the exponential function. Solving for b requires taking a sixth root. You do that in your calculator by the method I showed you previously. Round your answer to 4 decimal places and go back and plug in a and b into your basic function, and then your function is written for that scenario. So if you want to give one of those a try, I encourage you to pause the video, see if you can get what I got. This is the identification of the 2 input-output pairs along with the function I wrote as a result using the same method that I just showed you. The last example for the day is going to be writing an exponential model when we do not know a. All right, so here we do not know the initial value, so there's going to be a significant amount of algebra involved in order to locate both a and b. So let's remind ourselves that the general exponential function looks like this. F of x equals a times b to the x. And so what I am given is 2 input-output pairs, x and a y, and another x and a y. Or in terms of what we see at the top, this would be f and f of x, right, which is equivalent to y. But we are using that function notation because it does ask us to find an exponential function and not an equation, in which case we would use y instead. So in order to do this, I'm going to have to write 2 equations, one with each input-output pair. So I'm going to label the first one, star show up in the video. All right, so we're going to write 2 equations, one with each input and output pair. So equation number 1, we'll use the yellow highlighted input and output pair, and that will be 6 equals a times b to the negative 2 power. In equation number 2, we'll use the blue highlighted input pair, and we're going to write that as 1 equals a times b to the 2nd power. All right, now that you have 2 equations, we are going to solve this system of equations to figure out what a is. And so how do we need to do that? The first thing we're going to do is we're going to solve equation 1 for a. Okay. All right, we're going to solve equation number 1 for a. So starting here, I have a, b to the negative 2. The first thing I want to do is handle that negative exponent. Recall a negative exponent does drop into the denominator and become positive, so I end up with a over b squared. My next step will be to multiply both sides by b squared. I'll have 6 times b squared equals a. And now I've solved for a. We're going to call this, just for reference sake, because we will come back and use it again later, I'm going to call this equation 3. So now I want to substitute into equation number 2 and solve for b. That's one method of solving a system of equations, is by substitution. So I will substitute the a I just found into equation 2, which will enable me to solve for b. Substitute equation 3 into equation 2, and then solve for b. So 1 equals a. You'll recall a is 6b squared times b squared. So now I end up with, by the properties of exponents, 6 times b to the fourth. And we're going to end up solving, again, with a root that's not a square root. So let's isolate b first, and I'll end up with dividing both sides by 6. I'll end up with 1 over 6 is equal to b to the fourth. And in order to solve for b, I will need to take the fourth root of 1 over 6. And that process in your calculator is exactly like it was before. And you'll obtain to the nearest 4 decimal places that b is approximately 0.6389. So I now have a value for b. So I'm going to go write that up here because I'm going to need it later. So the b value, I have a number, so I want to record that number because I'm going to use it to write my equation later. 0.6389. So the only other value I need now is a. Remember, I need an a and a b to write an equation. But recall that equation number 3 is already solved for a. We simply have to plug in the numeric b that we've already found. So now I want to plug in b and solve for a. So in order to do that, we'll say, all right, we have a number for b now. So this is 6 times 0.6389 squared. And simply evaluating that will give me a value for a. And so a is equal to approximately 2.4492. And now that I've obtained a value for a, I'm just going to record that here just so I can keep my work nice and organized. Then I will take the two things I originally was seeking, the initial value a and the growth factor b, plug them into my general format in order to write the function for this particular scenario. So this will become f of x equals 2.4492 times 0.6389 to the x power. And that is the function for an exponential model that passes through the two given points. Now that process has a whole lot of steps, but I'm going to run back through it one more time just in case. So again, I'm given 2 points. I do not know the value of a. I need to remember that in order to write an equation or a function for an exponential scenario, I need an a and a b. In order to do that, I have to write two equations using the input-output pairs that I'm given. Solve the first one for a. Take the resulting equation and plug it into equation 2, and then solve that equation for b. Using this process, we will get an actual number for b, which I encourage you to record somewhere so that you can keep track of it. After you obtain b, you'll go back to the equation number 3 that you have already isolated a in and plug b in to get a number for a. Record that somewhere to keep track of your work, and then all that's left is to simply plug in the a and b that you found into the general exponential model, and then your function is written. Here is the graph of the function that we just wrote. Notice it contains both points. And now if you'd like to give this one a try, see if you can obtain this function given these 2 points, and you'll find that exact same process is going to work just the same. All right, so I hope this was helpful. We'll do some practice, and then we will set up the rest of this section to be done on Monday.